Good morning, my YouTube viewers. It is Crystal here, and in this video, what we're going to talk about is applications of estimations and statistics, and we're going to go over a few examples. So the first thing we're going to cover is estimation in descriptive statistics, because as you remember from previous videos, descriptive statistics gives you things like mean, mode, standard deviation, variance, range, things like that. So we're going to create a small little program to give you an example of how to use estimation in descriptive statistics. So the first thing we're going to do is we're going to generate the sample data, and we're going to initialize that by setting our seed to set.seed brackets 1, 2, 3. So every time you run the cell, then what will happen is the variables will initialize to the same values. And then we're going to generate our sample data. So X becomes our norm brackets 100, comma, mean equals 10, comma, SD equals 2. So that means you have a randomly sampled normal distribution of 100 samples with a mean of 10 and a standard deviation of 2. So we're going to set up our basic statistics. So mean X equals mean of X, and var X equals variance of X. And then we're going to example proportion greater, that with values greater than 10. So prop X becomes mean brackets X is greater than 10. So then what we're going to do is we're going to print our results. So we're going to print the mean, variance, and proportion, and you use the cat function if you have like text in with variables. So our mean is 10.18081. Our variance is 3.332931. And our proportion of greater than 10 is 0.52, because we set our normal distribution to have a mean of 10. And so what you want is you want everything greater than 10. So now what we're going to do is we're going to plot our data, and we're going to plot the data in the form of a histogram. So hist brackets X, break equal 15, color equals sky blue, main equals histogram of X with mean line, that's your title, X lab, which is the label of the x-axis, is values. So we're going to add a mean line, AB line brackets, V equals mean X, color equals red, line width equals 2. We're going to add a legend brackets top right, and then the legend is going to be mean. It's going to be a vector that has mean in it. Color is going to be red. It's going to be a vector that with red in it, and line width equals 2. So we're going to, we plotted this normal distribution that had 100 samples with a mean of 10. And so this is your mean of 10. And these are all of the samples greater than 10. Well, it's all of the samples. It's 50 samples. But the proportion of samples that are greater than 10 is 0.52 or 52%. So this is your histogram with X with the mean line. And you've got the mean in the center of the histogram. And it resembles a normal distribution because we actually did use a normal distribution that had been sampled 100 times with a mean of 10 and a standard deviation of 2. So now what we're going to talk about is how to use example of estimation in inferential statistics. And inferential statistics is more complex than differential statistics. So the first thing we're going to do is we're going to generate our sample data. So every time we run the program, the variables will be initialized to the same value. So set.seed brackets 1, 2, 3. So x becomes our norm brackets 50, comma, mean equals 10, comma, SD equals 2. So that means you've got a randomly sampled normal distribution. You've got 50 random samples with a mean of 10 and a standard deviation of 2. And then what we're going to do is we're going to create a hypothesis test, which is used in inferential statistics. So the null hypothesis is a mean is 10. So that means if the mean is 10, then that's your null hypothesis. So our test result becomes t.test. So you're going to perform a t-test, brackets x, comma, mu equals 10. So mu is the 10. And then we're going to, so you're going to perform a t-test on that with x and mu is 10. So extract useful values. Sample mean becomes mean x. Ci, that's your confidence interval, which we have discussed in previous videos, becomes test result $conv.int. P-value becomes test result $p.value. And then we're going to print the results. So we're going to print the sample mean, the confidence interval, and the p-value. So cat is a print statement, but it's a print statement that you use whenever you have variables in there, when you have like text and variables combined. So we're going to print off the sample mean, the 95% confidence interval, and the p-value. So your sample mean is 10.06881. Your 95% confidence interval is 9.542 to 10.595. So that means all of the values, well, 95% of all of the values are going to be between 9.542 and 10.595. And your p-value is 79%. So since your p-value is greater than 0.05, that means you're going to fail to reject the null hypothesis. So that means that you fail to reject the null hypothesis. So that means the null hypothesis is true, which means the sample mean is 10. And then so now what we're going to do is we're going to plot our data onto a chart. So we're going to plot brackets density x. So you're going to create a density plot of x. Main is density plot with mean and 95% Ci. Let me just check Ci. Let me just check something. That main is your title. X lab is your label on your x-axis. It's values. Color is sky blue. Line length is 2. And then so we're going to add a line for the mean. So AB line brackets V equals sample mean. Color is red. Line length is 2. And then we're going to add the confidence intervals. So AB line brackets V equals CI. Color is dark green. Line length is 2. LTY equals 2. We're going to add a legend. So legend brackets top right. Legend is going to be a vector containing mean and 95% CI. The color is going to be a vector containing red and dark green. The line length is 2. LTY is going to be a vector containing 1 and 2. So 1 means the line is straight and 2 means the line is dashed. So we plot the we plot the data, and so you have your density plot with mean and 95% CI. So your mean is at the center, being 10, and the confidence intervals are to the left and to the right with a 95% confidence interval. So that means 95% of the mean is going to be 9.542 and 10.595. So that is how you use the estimation with inferential statistics. So now what we're going to do is we're going to use estimation with regression analysis. So we're going to create a small little program to demonstrate this. So we're going to generate the sample data. First thing we're going to do is we're going to set our seed. So every time we run the cell, it's going to initialize the variables to the same values. So set.seed brackets 1, 2, 3, and then x becomes r norm, brackets 50, mean equals 5, SD equals 1. So that means it's going to be randomly sampled, normal distribution, 50 samples, a mean of 5, and a standard deviation of 1. So y becomes 2 plus 0.8 times x plus r norm, brackets 50, comma, SD equals 0.5. So this is a linear relationship with noise. So again, it's going to have 50 samples and a standard deviation of 0.5. So that's your noise. So we're going to fit the regression model. So model becomes LM. LM means linear model, brackets y squiggly x. And so that's the code that you use for a regression model. Then we're going to print our summary model. So when you print your summary model, this is what it's printed out in ours. It gives you a printout of the regression that you have just made. And the reason why it does that is because R is a statistical program written by statisticians. So now what we're going to do is we're going to make a prediction. So new x becomes data.frame, brackets x equals 6. So data.frame is you're going to create a data frame. Predicted y becomes predict, brackets model, comma, new data equals new x. So that's why you're going to make a prediction and on your model. And then again, we're going to print the prediction. So predicted y for x equals 6. And again, cat is a print statement where you have variables and text in there. So it says predicted y for x equals 6, 6.852. So now we're going to plot the data against the regression line. So plot brackets x, comma, y, comma, PCH equals 19, color equals sky blue, main, that's the title of the graph, is regression of y on x. X-lab, that's your label of your x-axis is x, and y-lab, that's your label of your y-axis is y. So we're going to add the regression line, AB line, brackets model, color equals red, line width equals 2. We're going to add a predicted point. Points equals new x, $x, predicted, comma, predicted y, PCH equals 19, color equals dark green, CEX equals 1.5. Then we're going to add a legend. So legend is brackets top left. Legend is going to be a vector created of data, regression line, and prediction. Color is going to be a vector that's created sky blue, red, and dark green. So sky blue goes with data, red goes with regression line, and dark green goes with prediction. PCH is a vector with 19 NA and 19, and LWD is a vector created with NA2 and NA. So we're going to print the graph, and you see here, whereas our legend is top left in this instance, whereas the legends that we've had before were top right, but this one is top left. So your data is your blue points, and so that's the samples. Your regression line is the red line, and basically what should happen to have a 99, 100% accuracy. What should happen is all the blue points should be lined up across the red line. But since all the blue points are not lined up across the red line, then that means the dots are not accurate. They don't have 99, 100% accuracy. And then your prediction is your green dot. So your prediction is actually falling on the red line. So it's falling on the predicted line, so regression line. So that means the prediction is accurate according to the formulas in R. So the difference between R and Python is R has inbuilt linear regression models, so you can perform linear regression in R without having to use any libraries. But Python is a general purpose language, so in order to perform linear regression in Python, you need to use a library that has linear regression functions in it, such as sklearn or stats models, or maybe even SciPy. So that's the great thing about R. Is R, you don't have to import any libraries. The linear regression is already built into R. So that's a good thing about R. So now what we're going to do is we're going to talk about estimation and survey sampling. So we're going to we're going to do this in R, and we're going to create a small little program to do it in R. So we're going to simulate survey data. So the first thing we're going to do is we're going to set our seed. So every time you run the program, it's going to initialize the variables to the same value. So you've got set.seed brackets 1, 2, 3. And then so n is going to be 200, becomes 200. So that is your sample size. And survey is going to be a data frame with income equals R norm brackets n, comma, mean equals 30,000, SD equals 8,000. So that's a numeric value. So what it is a randomly sampled normal distribution of 200 samples with a mean of 30,000 and a standard deviation of 8,000. So now you're going to have employed, this is your binary variable, equals R binom, brackets n, comma, size equals 1, comma, prob equals 0.7. So that means it's going to be a randomly sampled binomial distribution of 200 samples with a size of 1 and a probability of 70%. And now weight equals R unif, brackets, n, comma, min equals 0.5, comma, max equals 2. So that's a randomly sampled uniform distribution of 200 samples with a minimum of 0.5 and a maximum of 2. So that's the data frame that we have created for this exercise. So now we're going to calculate our unweighted estimates. Mean income UNW becomes mean bracket survey $ employed, mean bracket survey $ income. So that's going to take your income, and then your prop employed and UNW equals mean bracket survey $ employed. So that's going to be your mean of your employed. And then now we're going to calculate our weighted estimates. So mean income W becomes weighted mean brackets survey $ income, comma, survey $ weight. And prop employed W becomes weighted mean bracket survey $ employed, comma, survey $ weight. And then now we're going to print off the weighted mean, unweighted mean income, weighted mean income, unweighted employment income, weighted employment income. And then so we're going to print that off using the cat function. And you use the cat function whenever you want to print something out and you want to use text and variables. So we come over here, and so our unweighted mean income is 29,931.44. Your weighted mean income is 29,764.35. And your unweighted employment proportion is 69.5%. And your weighted employment proportion is 71%. So now what we're going to do is we're going to plot these values onto a chart. So bar values becomes C brackets mean income UNW, comma, mean income W. So that's your unweighted income mean and your weighted income mean. And names brackets bar values becomes C brackets unweighted, comma, weighted. So we're creating vectors to store that information. And then so bar plot, so we're going to create a bar chart, brackets bar values, comma, color equals C, brackets sky blue and tomato. And so that means you've got a vector with the two colors in it. And main is your estimated population mean income. That's the title of the chart. Y lab, that's your label on your y-axis is income $, and y lim is the limits on the y-axis is C bracket 0, comma, max bar values times 1.2. So it's going to be 0 to the maximum of our bar values times 1.2. And then so we plot that out, and you can see this is the graph that we have plotted out. So you've got the unweighted values and the weighted values. And the unweighted values are very similar to the weighted values because the income is 29,931.44 for unweighted, and the weighted is 29.764. So the values are very close together, and this is picked up in the chart. So that concludes this video. That concludes the examples of estimation and statistics. The next video will be another statistical topic with exploring statistics in R. And so I hope you decide to watch it, and I hope that you've got something beneficial out of this video.